Welcome to a new Voltlog. Today I'm going to be showing you revision C for this ESP32 based thermostat valve controller, and we're going to do some thermal measurements using my infrared PCB inspection thermal camera. We're going to be talking about resistor power dissipation a little bit, and I'm also going to be talking about the future of this project, some changes that I might do in a future revision, and ask your feedback in the comments below about these. As mentioned in Voltlog 395, where I showed the revision B, I wanted to do this rather small change and release revision C, just to see if it was possible to improve the thermals of the board, in particular how warm these current limiting resistor networks get during operation. Before I continue with the presentation, let me quickly ask you to smash the like button on this video if you find the content interesting. That should send me some good feedback. And while we are here, let me also mention that these boards were manufactured by PCBWay.com, which is the official provider of printed circuit boards for the Voltlog YouTube channel. You'll find the link to their website in the description below. These resistors are placed in series with the input of the triacs and with each status LED to limit the current from the ESP32 GPIO. And here is a schematic of how they are connected in revision B. I've used 100 ohm resistors in a 4 resistor network package, which is rated for 1/16 of a watt per resistor. And that is 0.0625 watts and a maximum operating temperature of up to 155 degrees Celsius. But this max power dissipation is only rated for up to 70 degrees Celsius ambient according to its datasheet. The triac LED forward voltage according to its datasheet has a typical value of 1.18 volts. So if we put that into a calculator, we have a current of about 21 milliamps driving our triac and a power dissipation of 0.0445 watts. Now remember, our resistor network pack is rated for 0.0625 watts, so we are theoretically under the maximum limit for power dissipation at just about 70% load from the maximum allowed. Here is a thermal image of revision B of the board, taken with my DIT Spectrum OWL PCB inspection camera, and this is like the perfect tool for the job. I can get high resolution thermal images of my PCBs. I can even zoom in and take clear macro shots thanks to this manual adjustment lens for focus, and I've reviewed this tool in Voltlog 384, which I will link on screen right now. I highly recommend you watch that video if you need such a tool for your lab. And at this point I had the board running for 30 minutes in an ambient temperature of 24 degrees Celsius with all of the 10 tracks switched on, the valve actuators all wired on, meaning maximum power dissipation on the resistor networks. And we can see the tracks are running pretty cool as expected, minding their own business. The AC to DC power brick shown at measurement point PT5 is also running decently at 40 degrees Celsius. PT1 is the discharge resistor for the input filtering cap, that's running okay as well. The hottest point is obviously on the resistor networks around 43 degrees Celsius, which is roughly 20 degrees above ambient. Now technically that is perfectly okay within the operating range of the resistor, and I would add within common sense safe limits. The board could run like this for long periods of time with no issues whatsoever. However, just as a small experiment for myself and for the pleasure of my viewers, I did this revision C, where I tried a few tricks to try and lower the temperature on those resistor networks through PCB layout techniques. So here is a view of revision C PCB layout. This is from KiCad, and the first thing I did was to split the load across these packs. I now have mainly 3 resistors used per each pack, which leaves some headroom in terms of power dissipation for each individual pack. The second thing I did was to increase the thickness of these copper tracks leading to the resistor packs, because copper is a good heat conductor. However, it's best if you have the ability to create islands or patches of copper, which work much better than these long tracks which I have here. For example, 4 small patches of copper added to the corners of each of these resistor network packages would definitely work better than what I tried. Another possible optimization on the board, which I have not done here, is to space the hot components apart as much as possible and add some cutouts in the PCB to allow for convection cooling, like I did here under the AC to DC brick converter. So what do you think? Did these changes that I implemented in revision C add any improvement by lowering the temperature of these resistor networks? Leave it in the comments below. Place your bets now, because I'm going to be revealing the thermal image of revC. So here it is. Now we can't really call that an improvement. A couple of degrees is pretty marginal. You could have that variation just from the test instrument error plus measurement setup. So I have to be honest with you, I was hoping for like a 5 degrees Celsius improvement at least. We didn't get that, but it's okay, because the board didn't need it anyway. It was just a fun little exercise, and I encourage you to play with design optimization features like these when you're designing stuff, because it can help you understand the importance and magnitude of the various features you put into your design. For example, the main takeaway from this experiment is that thicker, longer tracks don't really help much in terms of heat dissipation, and you'll find this mentioned in various app notes dealing with thermal optimizations in PCB design, and they all show how the heat transfer drops considerably once you go past about 1 inch of copper length. So for example, if you had to design a PCB heatsink for a low dropout regulator, instead of putting a very big copper plane, you're better off with putting 2 smaller copper planes, one on the top layer and one on the bottom layers, which are linked between them with some thermal vias. So with our little experiment finished, let's talk about the future of the valve actuator project, and I would like to address a few simple feature requests that I've received so far, and why some of them are possible and why some of them are likely never going to be implemented. First, I get many requests for adding more channels. The main constraint is that we don't have enough space in this enclosure to add more channels, and we really need to use this particular enclosure because it's way cheaper and easier to find than other types of enclosures. And personally, I wouldn't like to pay 10 times as much for a bigger enclosure, and at some point it might be possible to add a second daughter board with more channels that would sit on top of the existing 10 outputs, but then you'd also need to have like a GPIO expander chip, and once again the cost of the board would go up even if you just wanted the simpler 10 channel version. Next, I get requests about driving other types of loads, switching to mechanical relays or solid state relays for high power loads, but it doesn't make sense to do that. This project started as a valve actuator controller board, and it will stay that way. And these tracks are optimal for doing that kind of job and possibly driving other smaller resistive loads. There is no point to switching to another type of switch, no pun intended, that would be more expensive. We'll need a separate voltage rail to drive it, and would take up more board space, so you would end up with fewer outputs on one of these boards. Next, I get requests about having an external antenna option, and that's something that I will have available as an option starting with revC when it will start selling on Tindie. By the way, that's pretty soon, just waiting for a few missing parts and I can start working on a new batch of boards. So when ordering the new version on Tindie, you'll have the option to select the external antenna ESP32 module and have an external antenna with a UFL connector included in the package. Next, I get requests about having the LEDs visible from the outside. Because as it is, when you close the enclosure, they're not really visible unless you build some kind of light pipe to bring them to the top of the enclosure. And I have mixed feelings about this request. First of all, the LEDs are not really needed because this was designed to be ESP32/Tasmota compatible, thus using MQTT, thus using web config where you get live status of the outputs. So you don't really need these physical status LEDs. So what I'm thinking is to have them on a small daughter board that you can purchase separately and only use it if you really need them. And then you could like place that daughter board right on the top of the enclosure, and it will be connected via a short ribbon cable to the main board. But on the base version, I think you won't have any status LEDs anymore. It's just that from my point of view, it doesn't make sense to have these LEDs in here. And I think having them as an option, it's an optimal solution. But if there are any other upgrades that you think could be useful for this product, I would be interested in hearing your thoughts in the description below. Otherwise, this is the future I see for the board, and that's all I had to share in this video. Don't forget, you can support the channel on Patreon with as little as $1 per month to help keep these videos and projects coming, or you can just smash the like button because that's free. Thank you for watching, and I will be seeing you next time.